Okay, why is a Turing machine a real computer? And the answer for this question, of course, it is not. It's a model of computation. It's theoretical. You can build it in the real world, but why would you? We have much better computers than that, but it's a really good model to think about computing. But I do want to convince you that whatever program you can write that, do some computation, you can write an equivalent Turing machine that would do the same computation. It might be slower, it would be mind-boggling, undecipherable to understand what the hell it is doing, but it's possible. And if we had more time, I would spend way more time on doing example of Turing machine, building up the Turing machine to the point where I would convince you that it can do all the stuff that we need to really write a real program. Essentially, you build it up to the point where it's clear that you can simulate any CPU essentially with a computer. But I'm not going to do that because first it's mind-boggling tedious, and secondly, you can take it on faith. If you don't want to take it on faith, then there are a lot of texts out there that explain in detail how to do some of this stuff, or you can look online. In particular, I think people even wrote simple compilers that take a program in some simplified C and compile it into a Turing machine. So you can do, if you want to convince yourself of this point, it's easy enough to do. But it's easier to take it on faith. However, let me try and go through sketch out some of the steps on this way. Okay, so the first step is to build a Turing machine, for example, that add two numbers, right, in binary. So this is not very difficult because, for example, what you can do, you can take the alphabet of the tape and think about every cell of the alphabet as in fact being two cells, top part and bottom part, right? So what you can do as a first step is the input comes conceptually on the first part, right? Whatever number, dollar, whatever number that you want to add. And the first thing you can do is you can just copy the second number into the first number. Let's assume that they're in, order, the bit order from left to right to make things easy. So you can easily copy them to this, bottom part of the cells. And now they're aligned, and you can just go and from left to right end them up and write down the result. And this, by the way, brings forward the important thing that it's because the alphabet of the tape can be arbitrarily large, it's very easy to simulate where every cell of the tape is 20 cells, right? Once you have this, it's very easy to simulate, a Turing machine that uses 20 tapes instead of one tape, right? So we can easily simulate a Turing machine that have an arbitrary number of tapes with a Turing machine that have one tape, so it's an equivalent model. Now, once you have a Turing machine that have a constant number of tapes as large as you want, you can think about this other tapes as working space. You can think about some of them you can allocate as registers if you want to think about the CPU and so on. Maybe one of them would be a stack and so on. So you already get a much more general Turing machine, which is useful. It's not hard to show that you can do basic things like, copy the input tape one character to the right, duplicate the input twice, and so on. All those kind of basic copy-paste operation, which are very tedious but necessary for all this build-up. In particular, once you have enough tapes, it's very easy to show that Turing machine can support subrouting calls, right? Because you have a stack and you have registered, so it's all easy. You can pass parameters and so on. And as I said, hopefully, if you think about it for a while, you can convince yourself that you can compile, let's say, any reasonable program in C or Java into a Turing machine, right? For Java, really what you want to do is to just show that you can compile a Java virtual machine code into a Turing machine, which is tedious but doable. Okay, so from this point on, I'm just going to take it as an assumption the Turing machine can do whatever programs can do. And from this point on, I would like you to think about, whenever I say Turing machine, I just want you to think about the regular program, okay? And that's an important point, right? When Alan Turing wrote his paper in 1936, they didn't have real computers. They didn't even have the notion of execution, right? So Turing really had to define those very basic things, which was, of course, what he did in his famous paper. But we have intuition what programs can do. We know how to write programs, and so on. So it's much more convenient to think about programs. So whenever you read the Turing machine, think about the program, okay? From this point on. Unless, of course, you need to think about Turing machine explicitly. Okay. Now, as I hinted to earlier, Turing, amazing observation in considering the fact that he had no computers and he had to come up with this stuff himself. His brilliant observation was the realization that the Turing machine can simulate another Turing machine, right? Well, as I just said earlier, a Turing machine is just a number or just a string. An execution, the current state is just a number, so it's two numbers, and you can easily simulate the next step of the Turing machine, right? So this construction is this universal Turing machine that he described in his paper, which is in our language is like, yeah, well, of course you can write an interpreter for a programming language and just run a program on this interpreter, right? For us, this is a trivial observation. For Turing, that was a deep insight, which I think should really be appreciated. And that really gives you power, a lot of power, right? Because suddenly programs can rewrite other programs and do other bizarre things. Okay. So why do we speak about Turing machines? Maybe I should explain this because I sound a bit dismissive about Turing machines. So Turing machines are really simple. And as I hinted to before, just think about Turing machine compared to a modern CPU. Modern CPU is unbelievably complicated. And Turing machines are very, very simple compared to that. So it's a much simpler model of computation. We can understand what's going on. Everything is easy to describe, and we can easily argue about what can be done. So it's really a great sandbox for thinking about computation and what can be done with computation. But of course, I have to say that it's a completely counterintuitive model for us because we have real programs and real computers. And the surprising thing is that despite the fact that, already 80 years, or to be more precise, 84 years had passed since Turing wrote his famous paper, we don't really have a better model for thinking about computation. Not really. There are equivalent model using lambda calculus and functional programming and so on. But when you look carefully on things, they are not simpler. So it's really striking that this model, which is a bit clunky, frankly, this 7 tuple and all this nonsense, is still somehow the right way to think about computation, despite the fact that it's counterintuitive. Okay. But as I said before, I just want you to think about Turing machine as just being a program. Okay, so as I mentioned before, the next entity we will need for the next step is this universal Turing machine, which can do whatever it wants with other Turing machines, right? It's an interpreter conceptually that can run other programs or modify other program or modify other program into form, and they run other programs on them and so on, do this meta program execution. And this implies that you can do things like program can self-modify, right? Which, of course, is a big no-no in the real world. Although, it's a big no-no that was possible to do until 20 years ago, right? Nowadays, you really don't want program to modify themselves. It's really bad. And the important thing that we're going to use in the next step when speaking about undecidability and so on is that a program can rewrite a program. And that really was this observation that you have a universal Turing machine was really Turing's deep insight. And once you have this ability of programs to run other programs and write other programs, you really open a Pandora box as far as what can programs do. And this is a Pandora box that we will open, that Turing had opened. We will reopen it in the next lecture, and hopefully would learn something new. And that's it for today.